examples or maybe some.
Dear participants, due to technical issue, those who have removed from this meeting, you please join YouTube live.
Hello.
Yes, sir. Yes, sir. Please.
Now you have so many problems, you know. Now today,
yes, sir. No problem.
We are not expected this thing. Okay.
Yes,
let us see now. You know, our videos are visible or not. I don't know. Let us. I share my slide now.
Okay,
then
sir.
we'll think. Okay, sir.
Okay, sir. Okay, sir.
Now we'll see whether my slides are. My scholars are also here to help me because you know today we are having big time. Also, I am connected through Wi-Fi, sir. Now today. Okay.
Okay. Okay, sir. Okay, sir.
Okay. Entire screen will not read. Will not read Wi-Fi. Entire screen of purple thing.
So I'll birthday presents. So can
My slides are visible now?
Yes, sir. Visible, sir. Presentation mode, it is better, sir.
Yeah. 1 second here. Yeah, I will do it. And sorry, today extremely sorry.
Oh, yes,
Rajesh.
Sir.
Sir, no issue, sir.
No problem.
Entire screen ಮಾಡ್ತೀಯಾ ಎಷ್ಟು ಮಾಡ್ತೀಯಾ ಎಲ್ಲಿ ಬರ್ಬೇಕ್ರಿ ಇದು One second. Video open ಮಾಡ್ಬೇಕಿದೆ.
Yes, sir. 1 second, sir.
ಏನ್ ಬೇಕು ಹೇಳಿ ಹೇಳಿದ್ರು ಸರ್. Okay, now it is okay. Now we can finish up. Please. ಏನ್ರಿ ಹೇಳಿ ಎಷ್ಟು ಬರ್ತದ್ರಿ. Now is it okay?
Yes, sir. Yes, sir. Please, sir.
Can you please read what is there first slide?
Yes, sir. First, now it is second slide, sir. Nanotechnology, the role of micromachining.
Yes.
Yes, sir.
Extremely sorry for the participants. I
no
beg
problem,
apology. Okay, Rajesh, let us begin today. Okay. I divided my presentation into 2 halves. Okay, one is on the miniaturization of product and process, why it is very important, and what is the role of nanoparticles. Basically, I am concentrating on the mechanical micromachining techniques. Okay, this is the first part. Second part, very quickly we'll move on to the role of micromachining, particularly the finishing process, abrasive flow finishing process. How we'll use to avoid the bacterial adhesion to the implants. Okay, these are the 2 things what I am covering today. Okay, very good morning to one and all. Okay, I welcome you all for my presentation. On the and micromachining laboratory and research work and challenges. Then we'll move on to the role of miniaturization of product and process, why it is very important. Then we'll go to the micromachining technique, quickly the silicon-based and machine tool-based micromachining technique. As because, you know, this micromachining is basically developed for the MEMS devices from the electronic industries. Now we are using the same technique in the machine tool industry to do the same work beyond the scope of the silicon-based micromachining. MicroEDM, as we'll concentrate more on the nanoparticle generation and characterization of nanoparticles, basically the copper, aluminum and silver nanoparticle. And one more thing I will, today I will emphasize more on the hybrid process, what I will call electrochemical discharge machining, which is also used to generate the various features and nanoparticles of non-conducting engineering material. Quickly, I will show you all these things. Then we'll move on to the nano finishing for bioimplants and bacterial adhesion study. This is our laboratory. What you are seeing now is a precision engineering instrumentation laboratory, which is one among the many laboratories in Department of Mechanical Engineering. We are concentrating mainly on the 5 major research areas. One is control engineering, mechatronics, robotics, precision manufacturing, hydraulics and pneumatics. Whatever the list I'm given down, it is only limited. In all the areas, we are working in the many domains. Now, if you see this, these are some of the glimpse of the facilities developed in our laboratory. After seeing this, you will see we are not having any conventional machine tool to machine any workpiece material or any futures. All are tailor-made process. You will see here micro EDM, micro ECSM, hot air jet machine, extrude honing machine, all the things, whatever you are seeing, friends, it is all our tailor-made process. All our research scholars are using these setups on the tabletop to carry out the experimentation. Simultaneously, they will acquire the data and they will do all the analysis in the same table. This is one of the beauty of our laboratory. These are some of the robotics facility available in our laboratory. The self-guided vehicles, parallel manipulator, SMA actuated parallel mechanisms, and some of the EPUC robots and T3DX robots used for the collaborative work in the robotics area. One more important facility what we are having is a robot calibration test facility. That is a furrow laser tracker. What you are seeing is a furrow laser tracker. The cost of this machine is a DST sponsored project. It is for the workspace calibration and dynamic characteristics and errors in the robotic system we are detecting using this furrow laser tracker. The very simple it is, the furrow laser tracker will emit the laser light, which will trace the retrorefractor. What you are seeing is a retrorefractor here. There are various sizes of retroreflectors are there, which will always trace the retroreflector. You will get the coordinates in the data acquisition system, what you will call a dynamical software, which will give you the X, Y, Z, theta X, theta Y, theta Z. Meaning here, you'll see here all the ISO parameters, what I have shown here, all we have to calibrate in our laboratory in line with so many softwares. Also now, currently we are doing for the trajectory tracking. What we are seeing here is the EPUC robot it is, which is a programmable type and connected through the what we will call a Wi-Fi as well as Bluetooth. This is used to generate the particular shapes like a circular trajectory, rectangular trajectory. What are the problems we are facing when it will trace the rectangular type of objects. How to overcome this? Then we are doing so many simulation experimentation. You'll see here we are overcoming the cornering using the same EPUC robot by locating the center CG of the tracing point. Also, we are doing some of the graphical user interface, which will connect to so many robots. What you are seeing here is a obstacle avoidance robots or a cooperative robots for path tracking, which are all are connected through the Bluetooth, and they will trace any path what you are given in the user defined graphical user interface. You will get algorithms we are developing for this. For example, path planning and trajectory tracking, dynamic obstacle avoidance, reinforcement learning. Many algorithms we are developing for the robotic area also, our scholars. These are some of the papers where you will get a lot of information on how these robots, multi-robots are used in the obstacle avoidance, path planning, waypoint navigation, many work. This is what I am showing you here, waypoint navigation. This is a newer area it is, as because waypoints are the guiding control points in which only what you will define, friends, initial position and final position you will define. N number of obstacles you will place. What it will do, we are using the probabilistic roadmap. This is probabilistic roadmap is generating the various points, all are waypoints in which our robot will trace the optimal path to reach the destination, avoiding all the obstacles. Again, you will get some of the papers our research scholars are published in these areas. Then another one is image processing. We are using for detecting and tracking the mobile robots. This is actually one MTech scholar worked on this for the object detection and avoiding the obstacle through image processing it is. She used some log analysis. Again, you will get a lot of information on this paper. Now again, you will see our MTech students are doing very good way. They are previously you are seeing only it will avoid the obstacles. Now what we are doing, you will see here in this figure, the simulation work, what he did. It will circumnavigate the obstacle, then I will get the clear size and shape of the obstacle I encountered, then it will go to the destination. The Bagbone algorithm is a well-established algorithm to circumnavigate the obstacles. Now what we did is the same principle we are using the multi-robot systems. What it will do in multi-robot system, 2-3 robots will come near to the obstacle. As soon as 2 robots will detect the object, what they will do, one will circumnavigate in the clockwise direction, another will circumnavigate in the anti-clockwise direction. Every time they exchange the data, which is the nearest point to the destination. Then this will transfer to the previous robots. Then they will follow, no need to circumnavigate again. They will follow the least path to reach the destination, avoiding the obstacles. This is also a very important breakthrough in the multi-robot system. If you see here, if you are using the so many robots, the paths traveled and energy investment is very less. Okay. Then also you'll see again the very important general simulation where we'll get all multi-robot system. Whole objective is avoiding the obstacles and tracing the destination with the minimum point. Now again, in robotic area, many people are working. Here you will see we are using the reinforcement learning. We know that reinforcement learning, how it will work. You will define the final destination, then leave it. Then it will search the various alternative to reach the final destination. Again, it will avoid the obstacle. Here, whatever the red circle I am showing, it will avoid the obstacle and reach the destination. This reinforcement learning technique is one of the important techniques now people are using in machine learning. Here it will work, very simple principle. We are attaching some weights. If the robot will move away from the destination, it will get the negative rewards. If it will move towards the destination, it will get the positive reward. This way, the robot will do the n number of iterations. For example, you will see we defined here initial position, final position. So many obstacles we kept on the 2D platform. It did the 180 iterations to get the final destination. Now, what is it? We show the reinforcement learning, machine learning, deep learning playing a major role to implement the various control strategies in the mobile robots. One more, last year, one student worked on the autonomous lake robot cleaning robot. Here also we are using the drones and the data collection robots. Here you will see the methodology here. It will include the deep learning for object detection. Meaning here the drones will carry the camera. They will detect the what I will call waste on the river or any place where you are using the local coordinate system. Then it will transfer to global coordinate system. After detecting, what it will do? No, the trash collecting robots will move on the lake. They will collect and they will back to the destinations. Here also, we are developing the control algorithms, but these students, they worked only on the algorithm parts and they are simulated. Experimental part is not completed because of the COVID-19. Now, one more thing, what we are doing is, this is a reconfigurable autonomous sewage cleaning robot, what we are seeing friends here. Now, sewage cleaning is the biggest part in sewer cleaning because now people are manually, they are cleaning the sewers. It is very difficult because, dark place is there, atmosphere is not congenial to clean the drains. That time we developed what we will call the sewage cleaning reconfigurable robots. You will see there are so many links are there, so many joints are there. And here is the cutters are there. They will move autonomously inside the sewer. When you will identify the blockages, the cutter will cut and flush the water and then it will move in the sewers. You will get, again, they are developing so many algorithms. Again, you will get this autonomous sewage cleaning robot in the papers. Now, why I told you all this thing, apart from the micro machining, I not told anything. Now we'll concentrate today lecture on the only micro machining for the nanoparticle generation and finishing. The objective of showing this thing is we are working in different areas. join hands to you know quick start the research, be a part of research at IIT Madras, because a lot of things are available for you, and different way to join the IIT as a regular PhD, direct PhD, interdisciplinary PhD. Many things are there. Admissions are 2 times. One is the applications will open in February for the July admission, October for the January admission. Now quickly we'll move, friends, today on the nanotechnology and the miniaturization of product and process are the need of the hour now. Because now industries all are moving towards the smart manufacturing, what we will call a digital manufacturing, where all machine tools are handled through the internet, meaning through your what we will call mobiles. Correct? There is a technology now. The human handlings are very less, friends, now. Then also you will see in the biomedical industries, the many breakthroughs are taking place in the nanotechnology. I will show you some of the things what is going on in the next slides. Now we'll see nanotechnology is a very wide and difficulty to define it, because applications are very wide. Correct? Some of the common areas are nanomedicines are there, nanomachines, nanofluidics, nanoelectronics, nanomaterials, nanoparticles, nanopants, so many nanorobots, ferrofluids, many things. Also now people are working on the nanocomposites by adding the particles of size, nano size in the main MMC or whatever it is. Now you will see this, the larger number of biomedical applications. I will show you in the next slide what are the applications are there for the nanotechnology. Also you'll remember, friends, funding is huge to carry out the basic and applied research in nanotechnology. If you are having some idea to generate anything nanoparticle or what particle separations or what drug delivery systems, anything if you develop, the funding is very good from the DST to carry out the applied as well as basic research. Then you will see this, what is the meaning nano and what is the size in it. If the term nanotechnology was invented by Professor Norio Taniguchi at the University of Tokyo in 1971. Please remember, friends, nanotechnology or mechatronics or MEMS, all new technologies, including the robotics, are developed mainly beginning at the Japan, then widespread use by the other peoples. The original definition you will see is the production technology to get the extra high accuracy and ultra fine dimensions. That is dimensions in the order of 1 nanometer, means 10 to the power of -9 meter in length. The NASA also defined the nanotechnology in the functional parts, like a creation of functional materials or devices or systems through control of matters on the nanometer length and exploitation of the nano level phenomena and properties of the material to use for the various applications. Because size reduction, energy saving, many advantages are there in the nano materials. Here the particles, as we know, particles are smaller than 1 billionth of the meter. Now we'll see, friends, very quickly we'll see the early days how nanotechnology is used. Very old days, 400 AD, silver particles and gold nanoparticles were seen in the liquor glass cup kept in a British museum, showing the different colors when it is illuminated inside and outside. Again, here no animations. Also, you'll see, friends, early days painting are drawn from the gold particles, what you are seeing here. Similarly, 19th century photography, silver nanoparticles are used. In 1957, Faraday's how the metal particles affect the color of church windows. Meaning, basically, you will see this, the small metallic nanoparticles are infused with the what you will call the glass material. When it will radiate inside and different directions, they will give the different colors. That is a breakthrough. 1950 to 1960, you will see the small metallic nanoparticle in the micro and meso, they are invented. 1960 onwards, very huge breakthrough in the nanoparticles and ferrofluids. Now, recently, what they are doing? You'll see here, friends, some of the nanoparticles are used for the cancer-fighting nanoparticles. What you are seeing is a cancer-fighting nanoparticles and drug delivery systems. I will show you some of the things in our work also, how they will use the concept for the drug delivery. Then now recently, what it will show is if you apply the magnetic field or a plus or minus polarity changes, nanoparticles will reorient in the any direction. This is again very important in the drug delivery systems, and also the separation of the blood pellets when you are separating the blood pellets. So nanoparticles are the cornerstones of the nanotechnology currently. Recently, as I have told you, copper, aluminum, silver nanoparticles have gained a significant interest by the researcher because it has a wide applications are there. Copper and aluminum nanoparticles are synthesized using the various vapor phase reactions and liquid phase reactions. Now our work is on the mechanical micromachining technique because as old nanoparticles are generating through the various process like the what I will call thermal metal removal process, ball synthesis method. Many methods are there. Now, how your machining process is used to generate the nanoparticle by controlling the various parameters, we will discuss. The synthesis of nanoparticle using the advanced micromachining technique is not explored much currently. The present talk reports on the novel approaches to synthesize the copper, aluminum, silver nanoparticle in the liquid media. Nanoparticles are synthesized by controlling the various operating parameters like if you take any process, friends, not only microidium. In microidium, the general parameters are voltage, duty cycle, pulse on time, frequency. Like this, you use any process, if you control over these parameters, possible to achieve the nano-sized particle. That is the main motto of the present talk. Whether you will use abrasive jet machining or laser machining, if you control the parameter, process parameter closely, then possible to generate the nanoparticles of any metals and non-metals. Also, one more problem in the nanoparticle generation we are also facing is agglomeration and sedimentation of the nanoparticles. This is one of the great challenge for the researchers, how to overcome this agglomeration and sedimentation for the longer duration. If you keep the nanoparticle constant because the weight is more than the density of the water, they will settle down. To overcome this, what are the methods are available during the application of these nanoparticles is also the great challenge. During the process also, if you use some of the process, the particles will settle by themselves due to the weight. That time you will get if you analyze the solutions under the transmission electron microscopy or HRSM, they will show the agglomerated particles of bigger size. Now, next question is how to overcome during the generation itself. Then many papers are available to overcome this agglomeration during the particle generation using some of the surfactants like polyvinyl alcohol or polyethylene glycol, okay, belgum, and many ACG are used as a stabilizer. What they will do, they will, when the nanoparticle is generated, automatically these fluids, surfactants will help us to surround the particle to overcome the agglomeration of next particle generated by the process. Also, during the process, you may use the what I will call vibrators to overcome the nanoparticle. But all are instantaneous. If you keep the solutions for the longer duration, again sedimentation will take place. Before using for any application, only sonication, whatever you will call ultrasonication, everything is required. Synthesized nanoparticles where how you will examine means various methods are there: transmission electron microscopy, SAED pattern, EDAX pattern, UV-based spectroscopy, and many methods are there to evaluate the characters like size, shape, concentration. These are the various methods available to characterize the nanoparticles. Next is, some of the particle what we have generated in our laboratory before going to the setup. The mean size of the copper aluminum nanoparticles are found to be 6 nanometer to 10 nanometer with a narrow size distribution and a stable dispersion in the solutions. Here, basically, we are using the user-friendly fluid as a DI water. The plasmon peaks for the colloidal solutions have found to be appeared in the middle of UV range of the spectrum. Thermal conductivity and viscosity analysis we have carried out on the generated nanoparticle to suit for some of the applications where it required the heat dissipation characteristics or to overcome the friction between the two parts. The thermal conductivity and viscosity of the synthesized nanoparticles are found to enhance with respect to pure DI water. As I have told you, the beginning we started the particle generation of copper and aluminum with the DI water. Here we are using some surfactant to overcome the agglomeration, but we are comparing the results what we are getting, whether it is application or a size, shape, whatever it may be, to the base fluid as a DI water. If you we are carried out rigorous experiments on this. When you do the analysis of DI water alone, you will get the mean particle size is 800 to 1000. When you add the surfactant, as I have told you in the previous slide, it will avoid the agglomeration. Also, you will use the sonication during the process. The application suitability of synthesized nanoparticle for heat transfer application is studied by developing the setup in our laboratories. The experimentation reveals that the colloidal suspensions have the ability to transfer more heat in the existing heat transfer system when compared to the conventional fluid, as I told you, DI water. Then you will see, friends, in the nanotechnology, along with the science, calls for the various application areas. You don't think always a nanoparticle, nanomaterials, nanoprocessing and characterization, and nano products also, people are using this. Then before going to see how nanoparticles are generated using our microEDM setup, now as I have told you, now industries are moving towards the smart manufacturing. People are thinking for the miniaturization of product because it will give you the lot of advantages. Meaning here now miniaturization is a need of our, because it will provide the lot of functional benefits, like the miniature products are very simple, occupy the less space. If occupies the less space, then low power consumptions, then more flexible they are, and also saving in material and much more for this. So miniaturization increases the overall system efficiency, in one word, but at the same time it will pose the difficulty in transportation and handling the miniature products. This is a great challenge. Now people are suffering how to handle this part and how to transport the small miniature product. This is a big area where the scope of research work is still pending. Then you may ask me, why is this sudden development in miniaturization? As because customers' requirements are stringent, friends, more stringent, as because they will tell the property like an extraordinary property they want. High strength, high hardness, high fatigue strength, whatever you will tell nanomaterials or nanoparticles you will generate, the customer requirement are very huge. Their demands are very high. This is one of the thing. Then they want multifunctional property. One material, it will serve all the function what they want. Then also the whatever the material you will develop, as I have told you, nanocomposites are some of the nano MMC materials. They must be easily machinable or moldable to the required size and shape. Again, you will see all the properties are contradicting to the development of the nanomaterial or nanoparticles. Miniature features. Nanostructure, when you will develop, in that, if you want to do the, again, miniature feature generation is the biggest challenge. After all, nano level finish on the complex geometries. Because many free-form surfaces are there, if you see the aerospace parts. So the embedded with various simple and easy operations like smart products, complex 3D geometries. Then finally they will put customer is a low cost. All are, you will see all okay, will produce. But later he wants the cost of the product is very low. Then what to do now? This is a big challenge for us. Now competition exists worldwide to meet the customer requirements, what they are specified in the previous slide. Fabrication of the component with all customer required feature is very difficult, correct? As because now you'll see, friends, he's a part in the manufacturing system, meaning he knows every step how his product is manufactured and what type of material he used, what type of process he used. Everything he knows now in the smart manufacturing. Previously, he will give the order, manufacturer will develop and he will send to him. He has to accept it. Now, no way it is. Because customer will redefine the things if he is not satisfied during the process itself. Because he's a part in the manufacturing system. See now what to do now, friends. Now, so many things are there. Correct, in miniaturization of any product and process, even though it is a need of time, we have to do many things. As academicians, we have to concentrate more and more on the R&D issues. Currently, we have seen the tremendous changes in the factory layout. As I have told you, the advanced machine tools are available now, even to handle the more than 100 tools at a time. What is very important thing is synchronization of the various devices, because in the smart manufacturing, everything is connected through internet. Previously, it is inside the factory. Now it is connected to the globe through what we will call the cloud computing. Search for the new strategy development in energy saving, harvesting, and development of newer material and reduction in waste is also main theme. Search for diverse strategies and methodology for optimization of process parameters. Now, to solve this miniaturization of product and process is what we will call the micro machining or microfabrication or micro manufacturing technologies are there to do some of the things what customer want now. Now what we have to do, we have to use these technologies to create the futures or whatever it is, products. Now if you see this micro machining technique, friends, previously it is developed in the microelectronic industries where the chip size is very small, in which you have to implement so many components, like millions, billions of components are integrated in the small chip, silicon chip. You are seeing the processor development also. The size of the chip is very small. When it is 4-bit processor is introduced, 2,300 chips. Now you will get same size, but how many components are there, transistors, in terms of billions. Also we'll see the clock speed, all they are increased drastically. How it is possible? Only development in this micro machining technique. Previously they are using this for the silicon as a substrate. That's why it is called as a silicon based micro machining technique, and also the MEMS based micro machining technique. Here silicon is must. Here also you will see when they are introduced, they are using the bulk micro machining technique, what we will call the subtractive process. Meaning they will remove the material beginning layer by layer to get the final product. Now technology is advanced, now they are removing atom by atom, friends. Atom by atom they will remove, they will get the required products. If you will see surface micro machining, on the other hand, what we will call now newer technology, even though it is very old, in the mechanical micro machining, 3D printing is playing a major role. Additive process. Any part, complicated parts are able to generate using the additive manufacturing process. By putting layer by layer, as usual, surface micro machining, it is adding the material layer by layer to get the final product. Now it is atom by atom they are adding. Why they are doing this thing? Control over the material deposition or material extraction is close control over the size, shape, everything is possible. You may ask, why silicon, sir? Previously, now people are using so many metals. If you see why silicon, its hardness Young's modulus and yield strength is higher than your steel. Also, it is lighter than the aluminum and harder than the steel. Also, you'll see, friends, during that day, miniaturization of product, very small product, very easy to etch or whatever add using the silicon. Is only possibility is there that time. Later, one more process is developed at the Karlsruhe University, Germany, LIGA process. It is simply a deep X-ray lithographic technique. What you are seeing here, how they are manufacturing from the X-ray technique. This is particularly used for non-metallic also. Now, current tendency is now as a mechanical engineers, we have to focus on the machine tool based. If you see the machine tool based, we are also able to currently succeed in producing the micro parts using the same technology like a material removal process, what we will call subtractive process, bulk micromachining. Same technique, but only they are given as a renamed as a material removal process, as an old bulk micromachining process. Then you will see second one is a material additive process. Similarly, surface micromachining, where we are adding the material layer by layer or atom by atom to get the products. Here, what we are using is, we are using the machine tool as a base. They are keeping the different methods. Here, we are using machine tool as a base. Apart from this, also, if you see, friends, the parts are fabricated in one stretch using the microforming or a microcasting process also. Then another category is a nano finishing. What is this? Here also comes under the micro machining. Here the objective is a surface finish to get like the mirror finish by removing the material layer by layer or atom by atom. How close you are controlling, the objective is a surface finish, not the micro features. Quickly, I will show you the machine tool based. This graph will show you the micro manufacturing technique. What I marked here, the traditional process, like a micro turning, micro milling, micro drilling, many process. For the finishing, you will see the lapping, correct? But these traditional processes are having some of the drawbacks because they required the physical contact is there and well-defined cutting edges are required. And the most difficult task is the fabrication of these micro tools. Also, friends, these micro tools, when they will come physical contact, what happens? They will break. Chances of breakage is more. Even then, they are using for generating some of the futures, but drawbacks are these are the what we will call fabricating the tools. Again, how they will fabricate? Again, they will go for the non-conventional methods. What I have shown in the green color: electro discharge micromachining, electrochemical micromachining, laser beam micromachining, electron beam micromachining, ultrasonic micromachining. Here material removal is in terms of micron. Please remember, friends, here the objective is not on the size and shape of the object. The micromachining is particularly meant for the size of the chip. Size of the chip is less than 1 mm, it is called micromachining. You'll see our process also, don't think like a MEMS, they are developing very small parts. Here, no. Here, objective in the machine tool based micro machining, the size of the chip is less than 1 mm, then easy control to generate the small size or AD features. Okay, now currently we are working more on the non-conventional type. What I have marked here, non-conventional type process we are concentrating. But still some scholars are working on the turning process, but still in the conventional turning itself, we are facing a lot of issues. Now technology is moved ahead. Now atomic bit processing, as I have told you, ultra fine cutting. Here the vicinity of the chip in the size of 1 nanometer. That's because, it is extremely large density of energy density is required. Here, no other way for us. We are using the single crystal diamond tools. You'll see, friends, here in all the ultra precision machines, all are the conventional tool, they're very expensive. The cost of the machine tool itself is a crores. But if you develop using the technology, available technology like principles of process possible to generate the cost-effective things. And also here, the machining parameters are restricted in the during the developmental stage. But if you develop from the basic scratch, so many process parameters are able to vary based on your requirements. Quickly, you'll see here, then that's why we are telling you advanced micro machining technique. What are these advanced micro machining technique? We are using here also some form of energy, whether it is a mechanical energy or a chemical energy or a thermal energy to remove the material. Again, it is very important is by layer, the size of the chip is less than 1 mm. Then only it is possible to generate the features of required size to the required dimensions. Meaning here, friends, even though this machining process will take a lot of time compared to the conventional machining process, here close control on the precision is ensured. Here, as I have told you, this advanced micro machining, you'll see here 1 tree is for the micro or nano machining process. As I have told you, mechanical, thermal, or a chemical energy used to get it. And another objective is remove the material to get the finish. Finish is a second objective. Then you will see, friends, now people are developing the hybrid process by combining the advantages of the two processes and to overcoming the disadvantages in the other two processes, which will result in the hybrid micro or nano finishing process like electrochemical discharge micro machining, electro discharge micro grinding. Many, 2-3 processes they will club here to take the advantages of the two processes and to remove the limitations available in the other process. Quickly, it will show you the size range. What I am showing you here, micro molding to focused ion beam machining. This will show you the minimum future size generated using the various process. Started with micro molding, it is a 500 micrometer. Now we are moving to ion beam machining, what I have called 0.2 micrometer. And also you'll see that many advantages are there. Similarly, same disadvantages are there, each process. Rajesh?
Sir, this is Chandrasekhar, sir.
Yes, sir. Chandrasekhar.
Yes, sir.
Because I'm thinking, we are connected through Wi-Fi. We are online. Correct, sir? Correct. We are online.
Yes, sir.
Thank you. In between, professor, I'll call you. You tell me yes. Okay, only one. After half an hour, I will call you. Okay.
Yes, sir. We are following, sir. Thank you, sir. Thank you.
Yeah. Now let us see, friends, some of the micro machining facility developed in our laboratory. These setups are developed by our research scholars. It's not like a lakhs or crores. Maximum it is, what you will call thousands. Apart from the other devices like the power supply and oscilloscope, all these things. Let us see now to develop the EDM cell. I hope that, assuming that all are mechanical engineers, we know this EDM cell basically consists of, the workpiece, tool feeding mechanism, and operating parameters. Correct, friends? Using this, what is the basic mechanism of material removal in EDM is the melting and evaporation of the workpiece material. The advantage here is a tool and workpiece are always maintained at the certain gap, what I will call gap breakdown. Always there is a gap between the tool and workpiece, assumed to be 25 to 50 micron. Due to this, you are able to machine the workpieces using the spark alone, correct? And these two, the tool and workpiece, are dipped in the dielectric fluid. The dielectric may be the anything, as I have told you, the DI water, transformer oil, kerosene oil, blah, 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 blah. Thing is, the dielectric fluid now makes us to develop the nanoparticle in the. Our scholars are working in the different media to generate the nanoparticles. Then if you see the tool feeding mechanism, as I have told you, as the gap between the tool and workpiece increases due to the machining, then we have to feed the tool. There are various methods are there to starting with servo motor to inch-wire motors. Many things are available in the market. Now our work is feeding the tool as the machining gap increases to maintain the constant gap. We use the PZT, that is a piezo actuator tool feed mechanism we are developed. Again, you'll see, friend, this is a patented work along with the nanoparticle generations. This is what you will see is a in-house developed micro EDM setup. Can you please tell me here the setup is there? You will see there are the seem to be the very big setup is very small here. It's a very, very small setup. It is having so many accessories like a power supply, data acquisition, electronics, many things are there, on this, but setup is very small here. Now I will show you some of the animations to you people. Okay, very quickly. Chandrasekhar sir, you are seeing this setup?
Yes, sir. Yes, sir.
Now I will whether it is okay. You will see now.
Sir, you can open, sir. We can able to see, sir.
Yeah,
Yes,
just now see, sir.
yes, sir.
Thank you. Because the objective, see, now it is seeing, sir. Professor, seeing?
Yes, sir. Yes, sir. Perfect, sir. Perfect.
Now you'll see the whole process is control. This is a copper plate she is machining now using the PZT actuated tool feed mechanism. Other things are the accessories itself. Replay beta. Okay. 1 second. Yeah. This is for she is increasing the voltage to visualize how the material is removed. The same it is. She see, friends, here it is a PZT actuating tool feed mechanisms. To enhance the machining operation, we implemented what I will call recirculation systems. Move on to this very quickly, friends.
Yes, sir. Yes, sir.
One more thing is, now you remember, now I'm showing you one very important diagram, cause and effect diagram. Any process will start working on this. This is a very important thing, cause and effect diagram. Our scholars are doing this for 1 year to develop this. What is the objective here is, what are the input parameters to the process? For example, here I'm showing you medium. What are the electrical parameters are affecting to the process? Tool parameters and the non-electrical parameters and the workpiece parameter itself. And they are studying the output responses like a MR, TWR, surface finish, recast layer, taper angle, and a radial overcut. And also this process is used for generating the what I will call channels and the various textures. I'll show you in the next slide. This cause and effect diagram is a very, very important to start with any process, which will give you the glimpse what are the input parameters and what are the output parameter. If I vary the voltage, what happened to output response? If I will decrease the capacitance, what happened to output response? These things they are developing the cause and effect diagram. They will take 1 year to do this by seeing all the literatures. Now you see some of the machined holes. I am showing you the machined holes on the silver plate. Here you will see, friends, these are some images, what it will show you. These are carried out for the different parameters. You will see there are the different parameters are there. If I will vary the voltage and frequency and the T on, meaning indirectly it is a duty cycle, if you vary, what happens to the size, shape, and then what they will call recast layer and many things they are studying in the process. Similarly, you will see the copper machined holes using the EDM process. And also to overcome the what I will call the tool wear, they are coated with the NIT coating, nickel phosphate coated tools used to machine the various hole. Again, she carried out the 16 experiment with the varying process parameter. Here the concentrate more on the tool wear, how it is affecting. Now you will see now here, friends, now it is some images will show you the effect of process parameter on machining the channels, straight channels. Then depth also they are capturing using the optical profiler. It is a non-contact mechanism. It is. They will measure the width of the channel and the depth of the channel along with the array value. Right? These are the some of the channels machined on the conducting material. Already we know that EDM is meant for machining the conducting material. We are machining the various channels. You see Y channels you are seeing on the silver plate and copper plates. These are used further. Further they will use these things to study the flow through these channels. Then what is the depth and what is the surface finish in the each wing, how it affects to the flow study. This they will study in our laboratory itself. This will show the some images with multiple passes, what is the depth and why the surface finish is different. bacteria affecting to the surfaces based on the surface roughness and topography of the machine surface. What is our objective now is we are taking the some of the biomaterials subjected for the different surface finish, and then we are planning to grow the bacteria. Then we are studying which surface is giving the less bacterial growth. Here objective is less bacterial growth on the finished surface. For this we are developed the one setup. I'll show you in the next slide. Whole preamble of this talk is bacterial adhesion and implant surface is one of the major concern, and it leads to biofilm formation, infection, failure of the implants. Please note, friends, the surface properties of the implant like a surface finish, surface topography, surface energy, chemistry playing a major role. Many literatures reveals that the irregularities present on the implant surface, that is a rough surface, exhibits a greater surface area with the depression, providing more favorable sites for bacterial colonization and biofilm formation. These roughness parameters are making the very good place for bacterial to grow in the logarithmic scale. As I have shown in the first slide, will go very quickly on these areas where rough surfaces are there, spots are there, and any cracks are there, any channels are there, small channels, micro channels I am talking. Bacteria are easy to grow. So also they will show that ultra smooth surfaces did not favor for the bacterial colonization and biofilm formation. Now, how to enhance this? There are several surface finishing techniques are available to alter the surface properties. As I have told you, the implants exhibit a freeform surfaces which are difficult to finish with the available conventional method. No other way now. Now we have to go for some other method to machine these freeform surfaces. So in today's talk, as I have told you, IL has developed a unidirectional abrasive flow finishing process. I'll show you, which is used to machine the biomaterials like a stainless steel SS316L and titanium alloy Ti6Al4B ELI. These are all what I will call it. These materials are frequently used in the bioimplants of hip, knee, anything, any shoulder joints, all. Now we carried out to the machining process to generate the different surface roughness purposely and to show the how our finish will enhance us the performance of the implants. Quickly, you see, friends, the purpose of this study is to evaluate the performance characteristics of the developer process. Like we are using the optical profilometer, scanning electron microscopy. Then goniometer is used to ascertain the wettability characteristics. As I have told you in the previous slide, bacterial adhesion is also due to the surface characteristics like a surface and hydrophobic surface. To study the hygroscopic surfaces, wettability study is very important, which is carried out using the goniometer study. Further, the machined surface are subjected to the bacterial adhesion study, in which, as I have told you, E. coli bacteria and S. aureus bacteria are grown on these machined surfaces. In conclusion, the obtained results demonstrate that I'll show you the results now. The developed UAFF, meaning unidirectional abrasive flow finishing process, is the need of time to alter the surface characteristics of the bioimplants, which are generally the freeform surfaces, and to reduce the implant-related infections and early implant failures. Already we know that the significance of surface finish is enhancing the not only aesthetic aspect, also the functionality of the process. This can be done in the conversion process. Already we know that this conversion process, getting the part is one using what we will call material conversion. Then finishing is very important. It is an added advantage. Also, it will, remember, friends, it will add the cost to the manufacturing process. This is a major part. The converting raw material into final product is very easy in the conversion process. But after adding this functionality, property, or aesthetic aspect, people are spending a lot of money in the finishing. The characteristics of finished products, various things are there. Here I am showing the size, geometry, surface topography, surface integrity, how it affects to the various functionality in the component, whether it is a lubrication, vibration, power density, or a torque, heat generation, all parameter what I am listed here depends on the surface characteristics of the machine surface. How to enhance this, the machining performance is already we know that various process like so many processes there. Here I am showing you the different process starting with the plasma cutting to what I will call cold rolling and drawing process, in which it will show the average surface roughness if you use a different process. Meaning whether it is a laser machining, electron machining, or a whatever reaming process, milling, they will give you the certain RA values. To further, no other way we have to use for the various process. Here it will show you this graph will show you very interestingly surface finish and tolerance limit, how it enhances the machining cost, the total machining cost during the MLT stage. Then what it is, there are the various process, hard turning, surface roughness, how when we move towards the lapping and polishing process, passing through the super finishing process also. Grinding, what is the range of RA values are. Based on the requirement, you have to use the process to get the surface finish. Already we know that grinding and lapping, honing, how they will perform, and critical components machined using the various finishing process. Now quickly, our thing is the abrasive flow finishing process. What is this here? What I am doing is a semi-solid abrasive media, a viscoelastic polymer media. Viscoelastic is a kind like a rubber material, which is impregnated with the abrasive particles of required size, what you want. Starting with the bigger size and ending with the smaller particle size. Then use this media to remove your flaws or what you will call peaks and valleys in the machine surface. Now what is this? This process you will see here, this is a polymer media which I am forcing through the workpieces. You'll see here in the other sketch where the abrasive media impregnated with the what we will call viscoelastic polymer is moving through the multi holes on the workpiece. If you'll pass this media again and again, recirculate this media through the workpieces, as the number of pass increases, the finishing will increases, and one time, meaning after 7 pass or 6 pass or whatever it is, what you want surface finish, you will get the mirror-like finish. I'll show you how it is. There are the different methods are there, one-way process, two-way process, orbital process, meaning the workpiece will held here and pass the media in unidirection. It is very good because if you see the surface texture produced on this, all are unidirectional. In the layer by layer you will get on the finished surface. In two-way process, what the people are doing is they're pushing the media in one direction and other way they're pushing. Workpiece in middle between the two cylinder, they will push here and there. Meaning the stroke length is also very less in the two-way process. They will get up to 50,000 cycles. But in one-way process, you based on your length, how much you are extruding will matters. 6, 7 pass, you will get the very good finish. This is very difficult to produce in the two-way process. In orbital AFM, what they will do, the media is again they will transfer through the workpieces, but they will apply the magnetic field to reorient the abrasive particle in the required direction to finish the workpieces to get the similar effect as you will see in the one-way process. There are various variants are there on the AFM process. These are some things that I have told. Then again you'll see, friends, the objective is a finish, and what are the process parameters here? Maybe the different types of abrasive may you try, viscoelastic polymers you use, different varieties are there. Then additives, how much you are adding, percentage, concentration, all. Again, you know, the metals, what you are using in the machining, that will matters, geometry will matters, manufacturing process will matters. While machining the workpiece machined with your simple turning is different from a CNC turning, correct? Which workpiece is the input. Ultimate aim is what? To study the surface morphology, geometrical variation, wettability characteristics, and bacterial adhesion is the main motto. Now, here there are the various process parameters. As I have told you here, we studied the thermal property using the thermogravimetric analysis. You know, so many things are there here. Heat flow analysis, mechanical property we studied, and rheological property also we studied, like a shear viscosity versus shear rate, shear stress versus shear rate, and many properties we studied. The rheological property, mechanical property, and the thermal properties of the abrasive media itself. This is for the abrasive media. All these properties are affecting to your surface finish. Meaning, after developing the abrasive media of required concentration and required quantity, it is subjected for the thermal property, mechanical property, and rheological property before using for the processing. Quickly, you will see, friends, as we know that, as I have told you, number of parameter is a number of cycles. As number of cycle increases, surface finish you will get very good. Roughness decreases. Pressure also different. How you are extruding this media through the workpiece will matters. Abrasive size, abrasive composition, media viscosity, and other parameters. Similarly, we studied the material removal in the other media. And various components are machined through the thing is various parts are there. They will machine using the aircraft process. This is a setup, what we will call unidirectional abrasive flow finishing process. This is a media, you'll see, friends, here. It is like a rubber-like media. This is a power pack which is used to push the abrasive media contained in the what we will call abrasive cylinder. There are two cylinders, friends, here. This is what we will call abrasive cylinder, in which the media is filled completely, which should be pushed through the workpiece using the hydraulic cylinder. I'll show you the animation, then you'll get the very clear picture how they will operate. And then, as I have told you, as the number of cycle increases, the 3 cycles, 6 cycle, 9 cycle, how your peaks and valleys are get reducing. How many cycles you will do until you get the mirror finish, you will simply recirculate this media again and again. This is what we will call the unidirectional closed loop. Unidirectional, why I am telling this, the media is passing in one direction only. You will see here now hydraulic cylinder is there, abrasive media is there. Abrasive cylinder to hydraulic cylinder. What we are doing here is the abrasive media is filled here in the abrasive media cylinder. Using this cylinder and pushing this media. Then it will pass through this workpiece, it will fall on the next abrasive media cylinder. Then as soon as it will complete this pushing, then it will go back to the original position. Then this cylinder 2 is pushing the media. Then here also one workpiece is kept. Again it will feed back to the abrasive cylinder 1. This cycle will repeat. No need to handle the manually. Otherwise, filling the manually, this viscoelastic polymer impregnated with abrasive is very difficult part it is. It is a semi-solid media it is. You have to take a lot of time to fill it. To overcome this, this is a hydraulic circuit where media will be recirculate how many cycles you want. You'll see, friends, here, how the media is going through the different holes or whatever the cavities. The path of least resistance will take first to finish and then the next resistance. Quickly, I'll show you here. Again, animation problem. Here also you have to click. See this, friends, nitrile collar in which we are pushing the abrasive media. Down one you'll see this is a acrylic block in which we made the convergent divergent nozzle to study the effect of moving fluid on the cornering at the throat section, how the material is removed, we are studying. ಫೋನ್ ಮಾಡಿ ಸರ್ ಕ್ಲಾಸ್ ಐತಿ ಕ್ಲಾಸ್ ತಗೊಳ್ತಾ ಇದಾರಲ್ಲ ಬೆಳಗ್ಗೆ 10:30 ಇವತ್ತು 6 ಗಂಟೆಗೆ ತಗೊಳ್ತೀನಿ ಅಂತ ಹೇಳಿ ಈವ್ನಿಂಗ್ 6 ಗಂಟೆಗೆ ಎಲ್ಲ ಹುಡುಗರು ಹೇಳ್ಬಿಡಿ ಫೋನ್ ಮಾಡಿ ಹೇಳ್ಬಿಡಿ ಅಂತ ಹೇಳಿ ಎಲ್ಲರಿಗೂ ಇಂಟಿಮೇಟ್ ಮಾಡಿ. These key friends here, now it is a hydraulic block which is machined using the abrasive flow finishing process. Here also you'll see when you push this, radial holes all are machined. See here now, how the media is pushing through this is the aerospace part, it is having different holes, how it is machining you'll see. Yeah. Professor Chandrasekhar sir, you are online?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Quickly, I will take another 10 minutes. No need to worry. Okay.
Okay, sir. Go ahead, sir. Go ahead.
Because I started delayed. No, that's why I'm telling.
No problem. Sir. No problem.
Now we see, friends. We conducted like many studies. First is a machinability study. We studied for the different workpiece material. You'll see, and also you'll see the beauty of the fixture, which will hold the workpieces at the time it is. We want to study the repeatability of this on the workpieces. We are holding these 4 workpieces at a time, whether it is the same material or different material. Then you will subject this for the analysis. Okay. Now we will see as I have told you, as the number of cycles increases, the RA value, Rmax value, all how it is decreasing as the number of cycles increases. You don't need to, sometimes, RZ is very important, sometimes Rmax is very important. And most of the time, RA they are taking, I'm showing you here, all the parameters, process parameters of the surface characteristics are reducing as the number of cycles increases. These are the, some of the 2D profiler images, how the each process will reduces the RA value before and after machining. The workpiece material, whatever, aluminum, brass, copper, mild steel. Then it is what I will call convergent divergent nozzles. The beauty here, you'll see, friends, here one more thing, the machined surface, what we are seeing, actually this is some steel, it is SS316 steel, what we are seeing here in this figure. To study the effect of the movement of this abrasive media on the throat section, you will get quickly the radius. This is very difficult to get this thing in your what I will call convergent divergent nozzle venturi meters. Venturi meters, sharp corners are there. But here in this process, you will get a smooth curved surface in the throat section. You'll see here some text what we are shown here is reflecting in the finish produced on the workpiece. Meaning, as the number of cycle increases, your RA value goes on reducing. Meaning, you will get the very good surface finish. You will get nano level finish also. Then also they studied in the convergent section what happened, divergent section what happens. And they're concentrating on the what I will call surface defects also. See here what I'm showing, this is a radius effect. This we are observed in the what I will call the transparent acrylic block where we machined. And then we used the SS316 and a TI6AL4V for bacterial study. This is machined with the, as I have told you, no need to use only one concentrated abrasive particle. We use the 220 to 420, 400 also. Meaning 220 is a 220 or lower is a what you call chorus. When you go for 400 and 600, it is a what you call fine smooth. Then we are machining with chorus, first chorus abrasive particle size 220, 45. Then we are using the 400, then you're using 500. Like this, you'll machine. What happens? SS316 will show you the decrease in the RA value it is. Meaning surface finish, we are getting the better. Also, we studied the hybrid. Hybrid means 50% 220 and 50% 400, which is very good. This subject these are showing the SS316 and AICTE-STTP optical profile images for the morphology studies. Deep structures, how they are removed. See, beginning it is the deep structures are there as received. After machining, all are removed. You see, before machining, all the structures are deep structures. After machining, the hybrid, all are removed. Also, this is the unidirectional nature. Then what we are doing is objective is to study the angle is, and theta is 0, it will flow, water will be split over that.